Hello everyone. So my name is Karthik Nagar. I'm a PhD student in the compilers lab, and I'll be talking about data flow analysis. So I mean you have guessed by now that data flow analysis is related to compilers, and I'm assuming that all of you have used compiler sometime or another in your education so far. Okay. So what is a compiler? So compilers is a piece of software which basically converts a program that's written in a source language like C, C++ or Java to a machine language which you can directly run on your machine. Okay. Now while doing this transformation, it's important that the meaning of the program or the program semantics are preserved. Okay. Now the compiler itself will not really understand what the program is doing and how it is doing it, but yet it should automatically transform this program into the machine language such that when the program is run, it does what the programmer wants it to do. Okay. Now it's almost impossible to test a compiler because in general there are infinite programs, and if you really want to test it, then I mean, how can you be sure that the compiler is going to perform correctly for any program that it has not seen so far. Okay. So it's impossible to test a compiler, and therefore theoretical proof is needed that the compilation process is being performed correctly, right? Which means that the program is actually doing what the programmer wants it to do. Okay. Now besides transforming the program from source code to machine language, from source language to machine language, a compiler also does something else. So it also performs optimizations. So what are these optimizations? Optimizations are code transformations which are performed by the compiler to decrease the program size and to make the program run faster. Okay. So once again, just like the conversion from source language to machine language, these transformations themselves must be semantics preserving, which means that they should not change what the program does. Okay. And these optimizations will generally target unnecessary or redundant computations, and they will remove them from the program in such a way that what the program does is not being affected. Okay, so here are a couple of simple examples of optimizations. So we have constant propagation and folding. So what happens is that if in a program a variable is guaranteed to have a constant value, then instead of that variable itself, you can replace all the uses of that variable with the corresponding constant. So the advantage is that if you have studied a little bit of assembly language or machine language, you will know that when a variable is used, then it has to be loaded into a register and then the computation must be performed. However, if you have replaced the variable with a constant, then it will be part of the instruction itself, and that's much faster than loading it from memory into a register and then so on. Moreover, constant propagation also gives the chance of folding. Okay, so in constant folding, if for example you have a mathematical expression in a program and you know that all the variables in the expression are constants, then you can perform that computation during compile time itself instead of runtime. So you'll basically only perform the computation once, and that's how you'll basically reduce the execution time of the program. Okay. So another example is code motion. So if you have an expression or a statement inside the loop, and if that expression is loop invariant, which means that it doesn't change from one iteration to another iteration, then you can basically move that expression outside the loop. So in that case, again, you will not be executing the same statement again and again because the statement itself does not depend on the loop values. Okay. So just to illustrate these two optimizations, here is a very simple example program. So this is a simple while loop, and so can you see what possible optimizations can perform? Can you see that constant propagation can be performed in this example? So for example, here y is a constant. So therefore x will be a constant and t uses x, so therefore you can actually replace the value of t, you can actually replace the value of x in this expression. Okay. So that's what we do, and we also perform constant folding. Okay. So that removes a multiplication and it removes an extra load and store. Okay. Now there is another optimization that is possible here. So x is inside the loop, but again in every iteration we will only assign a constant value to x, so therefore you can actually move x out of the loop. Okay. So these are the couple of optimizations that can be performed in this program. Okay. Now what is the advantage of this? Okay, so I encourage you to do this experiment yourself as well. But if we run the original program after increasing the loop value to a sufficiently high bound, then the original program takes a running time of 4.3 seconds. But once you perform constant propagation and code motion, the running time reduces to 2.7 seconds. Moreover, GCC, the C compiler, also has its own optimization flag, which is -O2. And if you compile this program using the -O2 flag, then the running time goes down to 0.001 seconds. So you can see that basically using optimizations is very useful, and it greatly reduces the execution time of programs. Okay, so far I only talked about optimizations, but where does data flow analysis figure into all this? So data flow analysis is the theoretical foundation behind performing behind performing this compile time optimizations. So what is data flow analysis? So data flow analysis is a static program analysis technique to obtain information about dynamic properties of a program. So by static I mean compile time, and by dynamic I mean runtime. So the compiler can use data flow analysis in order to obtain some information about the runtime behavior of a program, and then it can use that information to perform optimizations. Okay, so the static properties of interest are generally related to the flow of data in the program. So you know that data is stored in variables. So what we are saying is that we are generally interested in properties about the values that are contained in variables. So for example, does a variable always have a constant value, or which other variables does a given variable depend upon? So these are the type of answers that data flow analysis will give, and then the compiler will use them for optimizations. Okay, so why is data flow analysis required? So again, this is for semantics preservation. So in order to perform these optimizations, the compiler has to absolutely know that by performing these optimizations, it does not change what the program does, and therefore it requires a guarantee on the program states across all executions. Okay, now it can't really execute the program with multiple inputs, because the number of inputs could be infinite, and therefore it has to use data flow analysis to give this guarantee. And data flow analysis summarizes all possible program states that occur at a program point across all executions in a finite set of flow facts. Okay, so we looked at these two optimizations. So what is required to perform these optimizations? So the constant propagation, it requires a guarantee that the variable must have a constant value across all executions, because only then you can replace the use of that variable with a constant. And code motion is going to require a guarantee that the expression is loop invariant, which means that the value of the expression does not change across all executions. Okay, so these are the guarantees that are required to perform these optimizations. Okay, so in order to illustrate data flow analysis, I will use a simple example of an analysis, which is the reaching definitions analysis. Okay, so first of all, let me define what is a reaching definition. A reaching definition. So a definition is simply an assignment. So any operation which is an assignment is a definition, and a definition D to a variable V, which means an assignment to V, reaches some program point P if there is a path in the program from D to P, and there is no reassignment of V along this path, which simply means that if there is a path from the definition T from the definition D to some program point V, and V is not being reassigned along that path, then you can say that D reaches V. So in the example, we have this definition D, y equal to 50, and we have this program point P, which is statement 4. So clearly you can see that D reaches the statement 4. So is there any other definition of y that reaches statement 4? So there isn't. So what about statement 5? So statement 5 uses z, right? So which definitions of z are reaching in statement 5? So you can see that z equal to 1 clearly reaches statement 5, but z equal to z plus 5 also reaches statement 5 because it's a loop. Okay, and the execution is going to flow from 6 to 3 again, and therefore z equal to z plus 5 is also going to reach statement 5. Okay, so you can now see that how reaching definitions could be useful for performing constant propagation, because so for statement 4 you can say that okay, which definition of y reaches this statement? So y equal to 50. That is the only definition that reaches, and therefore you can replace y with 50. Right. Similarly, at statement 5, which definition of z reaches it? Reaches this statement. So there are two definitions: z equal to 1 and z equal to z plus 5. but z equal to 1 is a constant, but z equal to z plus 5 may not be a constant. That's why you cannot replace z. So you can't perform constant propagation for z. Okay. Similarly, it can also be used for code motion. So for code motion, you have to ensure that the statement is loop invariant, which means that it depends on variables which are themselves loop invariant. So again, statement 4 is a loop invariant statement because y is being assigned a value outside the loop. So hence you can remove, hence you can replace or hence you can remove the statement 4 from outside the loop. Okay. So what do we need from reaching definitions analysis? So we need the set of reaching definitions that reach at each we need the set of reaching definitions at each program point, and once we have this, we can then use them for constant propagation or other optimizations. Okay. So to guarantee semantics preservation under optimizations, we need may reach definitions, which means that if ever there is some program path from a definition to a statement, then we must include that definition at that program point. Okay. If we miss some definitions, then that will not be safe, that will not be conservative, because we are ultimately going to use them for optimizations. So therefore, I will illustrate this later. Okay. But for guaranteeing safety, we need may reach definitions. Okay. So let's just go through what is required for data flow analysis. So assume that this set def is the set of all definitions in the program, and what we are going to do is that with each statement in the program, we will associate two sets, in-s and out-s. So in-s are the set of reaching definitions just before the statement s, and out-s are the set of reaching definitions just after the statement s. So basically with each statement we have assigned two sets, and in-s is going to be the set of reaching definitions, and out-s are going to be the set of definitions which are valid after the execution of s. Okay. Both in-s and out-s are subsets of def, and therefore they belong to the power set of def. Okay. Now each statement can generate a new definition and it can kill incoming definitions. Okay. So so each statement itself may be a definition. So that will be the statement that will be generated by s, and any other definition to the variable that is defined by s will be killed by s. Okay. So what it means is that if execution flows through this statement, then all the previous definitions to that variable are no longer valid, right? Because this variable has because this statement has redefined the variable. Okay. So gen-s and kill-s are the sets which are associated with each statement, and they are constants. Okay. So you can say what are gen-s and kill-s are by just looking at the statement itself. Now these are the two equations which are going to relate in-s and out-s with gen-s and kill-s. Okay. Now so we said that in-s is the set of definitions that reach s. Okay. So therefore you look at all the predecessors of the statement s, which means that all the statements that could occur before the statement s. So P is the set of predecessors, and you take the outset of each of the predecessor and simply say that in-s will then be the union of the outset of all the predecessors. Okay. Okay. And so once you know in-s, you know that out-s can now be related from gen-s, in-s and kill-s. Okay. So gen-s is the set of statements that is generated by s itself. Okay. So therefore you can say that out-s will be equal to gen-s union in-s minus kill-s. Okay. Because kill-s will be the set of statements that will be killed by the statement s. So you subtract them from in-s, and gen-s will be the set of statements, set of definitions which will be generated by s. Okay. So just to illustrate this further, here is our example program again, and I have annotated each statement with definition. So d1 is the definition z equal to 1, d2 is the definition y equal to 50, and so on. Okay. Now what are the gen and kill sets for all the statements? Okay. So again the gen state or the gen set will simply be the definition itself for each statement. So for example, for statement 1 the gen-s is simply the definition d1, for statement 2 it's d2, and so on. Okay. Now the kill set will be the definitions of the same variable which is being assigned by that definition. So for example, statement 1 assigns z, so I look at all the other definitions of z, so that's d5. So I will say that statement 1 is going to kill definition d5. Right. Similarly, statement 6 is going to kill definition d1, and for all the other statements the kill set is empty. Okay. So now you have, so now we have the in, okay, so now we have the gen and the kill sets. Now we'll just basically use this data flow equations. So we have the data flow equations here, in and out. So we are just going to populate it with gen and kill that we have defined so far. And we will have in1 equal to empty, and out1 will be equal to gen1 union in1 minus kill1. But gen of 1 is d1 and kill of 1 is d5. So I will simply assign the values to all the sets, and these are the set of equations that we will get, okay, for this, for the program, for this program. Okay, now if we solve this set of equations, so this set of equations is called data flow, is called a set of data flow equations. And if we solve these equations, then we will get the values of in and out, and once again the in values will show the set of reaching definitions before each statement. Okay. So our objective now is to solve this set of data flow equations. If we solve this, then we will get the set of reaching definitions, and then we can use it for optimizations. Okay, so again this is the algorithm that is used for solving the set of data flow equations, and it is very simple and very intuitive. Okay, so what you do is that you simply start with in and so you initialize in and out sets. Yeah. Out 5. Okay, so what I have done is that, see this so actually in 3 should be equal to in 4 should be equal to out 3, but since while doesn't do anything, I have simply eliminated that while, and I have said that in 4 will be equal to out 2 union out 6, because those are the two predecessor statements. Yeah, out 6 will be equal to this gen 6 union in 6 minus kill 6, and then in 6 will be equal to out 5. So that's how you relate the in and out sets. Okay, so I was talking about this algorithm, and so what we do in this algorithm is that we simply initialize the in and out of each statement to the empty sets, and then we repeatedly calculate this in and out set for all the statements. Okay, so what we do is that we initially start with empty set, then we then we have a while loop, and then inside the while loop for all statements we will execute these two equations, in and out set. Then we will see whether there is any change to the in or out set or not. If there is a change, then we will again do the same thing for all the statements. Okay, so we'll keep on doing this until there are no changes to in and out, which means that the in and out values stabilize, and we will say that and those in and out values will be a solution to the set of data flow equations. Okay, so there are some obvious questions now. So this is a very simple iterative algorithm which simply calculates this set of equations again and again. But how can we be sure that this algorithm will always terminate? Okay, because there is a while loop here, and it doesn't seem to have any bounds on it. So other question is like, how precise is the solution that is obtained by the algorithm, and in fact how do we characterize precision? So these are some of the questions that I will try to answer now. Okay, so in order to answer these questions, I have to go into a little bit of discrete maths, and that's lattices. So we have the set of definitions def, okay, in the program, and we have the fact that data flow analysis assigns a subset of def to each program point. Okay, now this power set of def, which is the set of all subsets of def, they form a lattice under the superset relation. So what is a lattice? So lattice is simply a partial order with the extra property that any two elements have a least upper bound and a greatest lower bound. Okay. So what you need to remember is that so a partial order is a relation that is reflexive, antisymmetric, and transitive, and a partial order basically orders the elements of a set in a way. Okay. So for example, so in this case, the power set of def forms a lattice under the superset relation, which means that you say that if you have two subsets S1 and S2, then S1 is less than S2 if S1 is a superset of S2. Okay, and we have and if def is equal to D1, D2, D3, then we have shown the reaching definitions lattice in the figure. Okay, so as you can see that so you have the empty element, which is a so every other set is a superset of empty element, so it's at the top. Then you have D1, D2, D3, which are singleton sets. Then you have D1, D2, in the third row. So d1, d2 is going to be a superset of both d1 and d2. So that's why it will be greater than both those elements. It will be less than both those elements, and so on. So the entire set def d1, d2, d3 is right at the bottom because it's a superset of everything. So it will be less than everything. So this is so remember that the empty set is at the top and the full set is at the bottom. Okay. So why have we defined this lattice in this way? So as you move down the lattice, your safety increases. So why is this so? I mean, this is because suppose the set of reaching definitions at some program point was actually the set D1, okay, but instead you said that okay, you calculated your data flow analysis, you did your data flow analysis, and you said that no, the set of reaching definitions is D1, D2, which is a superset of D1. That is safe, right? Because if you, for example, use D1, D2 to perform constant propagation, then it is possible that D2 may not be assigning a constant, but D1 is assigning a constant. So therefore you will say that okay, this statement is, so therefore I cannot use constant propagation here, right? But actually D1 assigns a constant, and therefore you can actually use constant propagation. However, that is just an optimization opportunity lost, right? It doesn't really change what the program does, okay? So hence, however, on the other hand, if for example the actual set was D1, D2, and D1 is assigning a constant to a variable and D2 is not assigning a constant, okay, but your data flow analysis concluded that no, D1 is the answer, then you are basically not safe, right? Because you will then say that okay, the value must be a constant, and then I am going to replace this value with a constant, but that is not safe because D2 may also reach that particular statement, and in that case it will not assign a constant value, and you will not get the same answer, okay? So in other words, as you move down in the lattice, you become more and more safe, but as you move up in the lattice, you will become more and more precise. So it will actually help you to perform more optimizations as you move up the lattice, but at the same time you have to be careful that you don't really go into unsafe territory. Okay. Okay. So we have the set of data flow equations here. How does it relate to the lattice? So any solution to the data flow equations is safe, right? Which means that it will basically be a superset of the actual set of reaching definitions at all program points. The iterative algorithm which we have used to solve this set of data flow equations, they compute the most precise solution if some conditions are met. So we will see what those conditions are. So which means that they will be as high as possible. The solution that is computed by the data flow equations is going to be as high as possible, but it is still going to be safe, which means that you can use it for optimizations without basically changing what the program does. Okay, and in general it is undecidable to compute the most precise set of reaching definitions for all programs. So remember that by solving the data flow equations you will get some set of reaching definitions, but the actual set of reaching definitions is you cannot compute it. I mean, the data flow equations will not be able to compute that, and it's undecidable to do it. Okay, so let's look at the data flow equations again. Okay, so now I will try to answer like why does the algorithm terminate, and what is the meaning of this most precise solution of data flow equations. Okay, so here we have the data flow equations again on the left hand side. So let us just collect all the LHS of this equation and write them in the form of vector, and we will collect all the RHS of these equations, and we will also write that in the form of another vector. Okay, so we have this vector of 12 values, in1 out1 to in6 out6, and it can be written and it is equal to some manipulation of those in and out variables. Okay, so this can be this can now be written as a function of in and out variables, right? Because it's simply doing some manipulations on the in and out variables. So we have this function f here, which depends on this in and out variables, this 12 in and out variables. And so what is this function f? So this function f is a function on the cross product lattice. So it basically takes 12 subsets of def, and it will give out another 12 subsets of def by basically performing these manipulations. Okay, now any solution to this any solution to the set of data flow equations is going to be a fixed point of the function f. So what is a fixed point of f? So an element x is called a fixed point of function if f of x is equal to x. So you can see that by applying f on the in and out variables, you are actually getting the same in and out variables. So So hence the in and out variables which will be a solution of this set of data flow equations are going to be a fixed point of the function f. Okay. So if we solve this set of data flow equations, then we will get a fixed point of f, but in general any fixed point of f is going to be a solution of this set of data flow equations. So what we will show is that the iterative algorithm is going to compute the most precise fixed point and hence the most precise solution of the set of data flow equations. Okay, so let's look at this algorithm again. So it starts off by initializing all the ins and outs with empty set. Remember I said that empty set is right at the top. So the in and out sets are initialized with empty, and if you remember the lattice, the empty sets are at the top of the lattice. Okay. Now you are basically now inside the while loop you are basically calculating this in and out sets again using the data flow equations, and one iteration of this while loop is equivalent to one application of the entire function f, right? Because that's what the function f does. It just manipulates the input in and out values to get some new output in and out values. Okay. So in other words, the iterative algorithm starts with top, okay, which is the empty set for all in and out, and then it computes f top, f square top, f cube top, until we reach some fi top where there are no changes to in and out, which means that fi top is equal to fi plus 1 top. So this is the fixed point. Okay, that's very clear, because if you apply f on fi top, then you will get fi plus 1 top, which is the same as fi top. Okay, so that's a fixed point, but it's also the most precise fixed point. Okay, and to understand why it's the most precise fixed point, we need another property of the function f. Okay, and that's that the function f is a monotonic function. Okay, so what is a monotonic function? So again, a monotonic function f. So a function f on a lattice L is called monotonic if for all elements x and y, if you have some relation between x and y, say x is less than y, then f preserves that relation, which means that f of x will also be less than f of y. So f is a function from L to L, and the lattice L is arranging the set, is sort of a partial order on the sets, on the elements of the lattice, and if you have two elements x and y, then, and if x is less than y, then f of x will be less than f of y. So the function f, the capital bold F, is also monotonic, and that's because it basically consists of this function gen union s minus kill type functions, and it's very easy to see that this gen union s minus kill functions are monotonic, right? If you take two elements, if you take two sets, say s1 and s2, and if s1 is less than s2, then in our lattice it means that s1 is bigger than s2. Okay, it's down, so therefore s1 is going to be a superset of s2. You are then subtracting kill from both the sets, so again s1 minus kill will be a superset of s2 minus kill. Then you are adding gen to both the sets, so again gen union s1 minus kill will be a superset of gen union s2 minus kill, and finally this is g of s1, so g of s1 will be less than g of s2. So in other words, if s1 is less than s2, then g of s1 is less than g of s2, and our function capital F consists of this function g, right, different functions g. Okay, so therefore the function f is monotonic. Okay, now so we have seen that our algorithm computes a fixed point in this way, and we have seen that the function f is monotonic. So let's just start with and we want to prove that by using the iterative algorithm we will get the most precise fixed point of f. Okay, so we know that any other fixed point of f is also going to be a solution of the data flow equations. Okay, so we start with some other fixed point of f. So let x be another fixed point of f, and we know that x is going to be less than or equal to top, because any element is less than or equal to top. Top is right at the it's right at the top of the lattice, and x is some other element of the lattice. Right? It's a fixed point, but it's some other element of the lattice. So therefore x is less than top. Now you apply f on both sides. Now here is where you use the fact that f is monotonic. So therefore if x is less than top, then the function f is going to preserve that relationship. So therefore f of x is also going to be less than or equal to f of top. Now you know that x is a fixed point, so therefore f of x will be equal to x. So hence x will be less than or equal to f of top. Okay. Now you can use induction to show that again you apply f on both sides. So you will have f of x is less than or equal to f square of top, but again f of x will be equal to x and so on. Okay. So in general you can show that x will be less than or equal to fi of top for all I. Now you know that the iterative algorithm is going to compute some solution of the form fi of top, but x is less than fi of top for all I. So that shows that any other fixed point is going to be smaller than the fixed point that is computed by solving by using the iterative algorithm. So that shows that basically the data flow equation, the iterative algorithm is going to compute the maximum fixed point of f. Okay, and the proof of termination again is very simple. So all of this uses the fact that that the iterative algorithm starts with top and then it computes fi of top, and the fact that the function f is monotonic. Okay, so again you have top and you have f of top, but you know that f of top will be less than or equal to top because f of top is just some other element of the lattice, therefore it's going to be smaller than top. Again you apply f on both sides, so use the fact that f is monotonic, it's going to preserve this relationship, so you have f square of top which will be less than f of top. Okay, again by induction you can show that this means that the top will be greater than or equal to f of top, and it will be greater than or equal to fi of top for any I. Okay, so basically by applying the function f you are going down in the lattice. Okay, but you can't go down infinitely because there is no infinite descending chain, right? It's a finite lattice. So every time you apply f you go down, but ultimately you will have to stop somewhere, right? Because the lattice itself is finite. Okay, so this basically shows that and once you stop at a point you will have fi of top equal to fi plus 1 of top, and that will mean that you will have calculated the fixed point. Okay. Yes, but if we remain the same point, that means it's a fixed point, right? Either we will go down or we will remain at the same point, and once we remain at the same point, it's a fixed point. So therefore the algorithm will terminate at that point, right? Because it says that if there is no change then you will terminate. So this shows that the iterative algorithm is also guaranteed to terminate, and once it terminates, by this proof you have the fact that it is going to compute the most precise fixed point that's possible. Okay, so let's just quickly summarize what we have seen so far. So in general a data flow analysis framework is going to consist of a domain D, which in our case was def, okay, and a relation under which the domain D will form a lattice, and a transfer function f, which in our case was this gen and kill sets, using gen and kill sets, and this must be monotonic in D. Okay, so if these conditions are met, then we have shown that the iterative algorithm for data flow analysis, it's guaranteed to terminate, and it will compute the most precise solution of the data flow equations, or the maximum fixed point of f in D. And moreover, so this proof I am not showing, but it can also be proved that MFP is also guaranteed to be safe. Okay, so I will just summarize now. So data flow analysis is used to statically obtain information about the dynamic behavior of a program, and the flow facts that are generated by DFA are used by compilers for performing optimizations. So we have seen two optimizations, constant propagation and code motion, but there are a number of other optimizations like copy propagation, dead code elimination, partial redundancy elimination, and so on. So each of these optimizations is going to require some input, and that input is provided by DFA. Okay, now the general framework of, so we have seen the general framework of DFA, and we have seen an example of DFA, the reaching definitions problem. But in general there are a number of different analyses like available expressions analysis, live variable analysis, and so on. And these analyses are just examples or instantiations of the general DFA framework. So we can basically reuse the iterative algorithm for DFA again and again for all of these analyses, and as long as those conditions are met, we will be guaranteed that the iterative algorithm is going to give you a precise solution. So as long as conditions are met, the iterative algorithm is going to give you the precise facts, flow facts, in a fast and efficient manner. Okay, and so all of this content has been taken from chapter 9 of the book on compilers by Aho, Ullman, and Sethi, and this is the standard reference book for compilers. So again, this is just an introduction to data flow analysis. I mean, you can see the examples of all this analysis in the book, as well as more optimizations are also given in the book, and detailed proofs are also present in this chapter. So you can read this chapter without any prior knowledge of compilers, because this is pretty much a standalone chapter. Okay, yeah. So that's it. So any questions?
So now we'll have a coffee break and then we'll meet at 4 with a lecture on randomized algorithms by Suprabhat Ghoshal. So we'll